Look up at the night sky. Go ahead. Really look at it. What you're seeing are photons, tiny packets of light, that have traveled across mind-bending distances to reach your eyes. That star you're looking at? It might have sent that light your way 10 years ago, 100 years ago. Some of the light you're seeing tonight began its journey before human civilization even invented the telescope. And yet, with all our technological advancement, all our innovation, all our dreams of becoming an interstellar species, we're still fundamentally stuck on this one planet. Now, you might think that's depressing, but I think it's actually the most honest scientific assessment we've made in a very long time. The latest generation of physicists, engineers, and astronomers have begun to quietly acknowledge something that earlier generations perhaps weren't willing to fully confront. With the laws of physics as we understand them, with the technology we currently possess, and with the biological constraints of human existence, traveling to another star system isn't just difficult. It's not just expensive. It's not even just unlikely. With our current understanding and current capabilities, it appears to be genuinely, fundamentally, perhaps even ultimately impossible. This isn't science fiction anymore. This is science fact. And it's beginning to reshape how we think about humanity's future in the cosmos. Now, before you close this video thinking it's going to be a downer, let me tell you something. Understanding why something is impossible is one of the most profound ways to understand the universe. It teaches us humility. It teaches us the true magnitude of cosmic distances. And it opens up a conversation about what humanity might actually need to do if we're serious about leaving our planetary cradle. Because here's the thing that's so fascinating about this realization. It's not that we failed to figure out interstellar travel. It's that the universe itself might be constructed in a way that makes it genuinely impossible for any civilization to cross the vast gulfs between stars. And if that's true, it changes everything about how we see our place in the cosmos. Let's talk about why the stars, it turns out, are much farther away than our ambitions. And I mean that not just in terms of kilometers or light years, but in terms of the fundamental physics that governs how objects move through space and time. When we really dig into the numbers, when we actually sit down and do the math without sugarcoating it, something becomes clear. The universe has built in some pretty serious roadblocks to any civilization that wants to venture beyond its home planet. Here's where we need to start, with distance. Not the kind of distance you understand intuitively, where you can drive for 8 hours and reach another state. No, we're talking about the kind of distance that broke the brains of ancient astronomers. We're talking about the cosmic scale. And I want to make sure you really feel what this means, not just intellectually, but emotionally, because understanding scale is understanding the universe. The nearest star system to Earth is Alpha Centauri. Now, you've probably heard that name before. Sounds close, doesn't it? It's called the nearest star system. There's something in that word that makes it seem like it's just next door. Like we could hop in a spacecraft and be there for lunch. But let me put this in perspective for you. Alpha Centauri is 4.37 light-years away. What does that mean? It means that light, traveling at 300,000 kilometers per second, the fastest thing in the universe, would take 4.37 years to get there. Light, the fastest thing we know of, would take 4 years to get there. Now let's think about a human spacecraft. Right now, the fastest object ever built by humans is the Parker Solar Probe. It's a spacecraft that was specifically designed to get as close to the sun as possible, and in the process, it's been accelerated to incredible speeds by the sun's gravity. Screaming through space at about 586 kilometers per second. That sounds incredibly fast, doesn't it? And it is. I mean, if you're on Earth and you're going 586 kilometers per second, you'd be traveling at roughly 2.1 million kilometers per hour. You'd circumnavigate the entire planet in less than 20 seconds. It's mind-bogglingly fast. But let me do the math for you. At that speed, 586 kilometers per second, our fastest spacecraft ever, it would take the Parker Solar Probe 2.3 million years to reach Alpha Centauri. That's not a typo. 2,300,000 years. Let me say that again, 2.3 million years. To put that in perspective, modern humans, Homo sapiens as we define ourselves, have only existed for about 300,000 years. So traveling to our nearest star at the speed of our fastest spacecraft would take 8 times longer than humans have existed as a species. Think about that for a moment. 8 times the entire span of human existence. Your species' entire history, every civilization you've built, every discovery you've made, every war, every work of art, every moment of love and triumph and sorrow. All of it would happen 8 times over before that spacecraft reached another star. And we're talking about the nearest star. There are billions more where that came from. Now, you might be thinking, okay, but that's because we're not going very fast. What if we accelerate more? What if we push our spacecraft faster? Let's imagine we want to send people there. Actual humans, not just a probe. We'd want them to arrive sometime in their lifetime, or at least in a time frame where the journey would be considered reasonable. Let's say we want a crewed mission to Alpha Centauri to take 100 years. That's a long journey, right? That would span 3 or 4 generations of people living on the spacecraft. 3 or 4 generations born, living their whole lives, and dying in a metal can in the void of space. Okay, 100 years to get there. How fast would we need to go? We'd need to travel at about 4.37% the speed of light. That's not 586 kilometers per second. That's 13,080 kilometers per second. We'd need to accelerate our spacecraft to nearly 8 times faster than our fastest spacecraft ever. We'd need to triple the speed of light from our perspective and then add some more. And here's the thing, we have no technology that could achieve this. No technology. Not even theoretically with near-future concepts. We'd need to fundamentally rethink propulsion from the ground up. We'd need breakthroughs that we haven't even imagined yet. And Alpha Centauri is the nearest star system. The nearest one. After we got there, if we ever got there, the next nearest star system would be Barnard's star at 5.96 light-years away. Then there's Luton 745-46 at 4.43 light-years away, which is actually closer than Barnard's. Then Sirius at 8.6 light-years. Then Epsilon Eridani at 10.5 light-years. The stars just keep going and going, scattered throughout space at distances that seem almost evenly distributed, like breadcrumbs thrown across an infinitely large room by some cosmic baker. And this is where the real problem becomes clear. Space is big. Incomprehensibly, mind-bendingly, soul-crushingly big. I've tried to use analogies to explain this. If the Earth were the size of a grain of sand, the nearest star would be miles away. If the nearest star were the size of a grain of sand, Alpha Centauri would be 1,000 miles away. These analogies help a little bit, but they don't really capture the true vastness of the cosmic scale. We're not dealing with distance in any way that human intuition has evolved to understand. Human intuition evolved on a planet. We evolved to hunt and gather across distances of maybe a few dozen kilometers. We evolved to navigate landscapes and understand how long it takes to walk from one place to another. But the cosmic scale is utterly beyond our evolved intuition. We're dealing with numbers so large they become meaningless unless we force ourselves to sit with them, to really contemplate them, to let them sink in. Okay, so distance is a problem. The universe is vastly larger than we can really comprehend. But let's assume we solve that somehow. Let's imagine some future version of humanity that's figured out faster propulsion. Let's imagine we've invented some miraculous engine that can push us to relativistic speeds. What's the next obstacle? Energy. Pure, raw, enormous amounts of energy. To accelerate a spacecraft to 1% the speed of light, just 1%, mind you, carrying a crew of 100 people, you'd need the energy equivalent of detonating billions of tons of TNT. And that's just to get up to speed. That's just the acceleration phase. You'd need to do it again to slow down when you arrive, because you can't crash into a star system at relativistic speeds. You can't show up doing 1% the speed of light and then just kind of gently float down to the surface of a planet. That's not a mission. That's a suicide mission. And if you're traveling even faster, 10% the speed of light, 1% the speed of light, faster still, the energy requirements don't just go up linearly. They accelerate exponentially. Let me put this in more concrete terms, terms that you can actually wrap your head around. All the energy humanity uses in an entire year, every power plant, every engine, every light bulb, every smartphone, every device, every manufacturing process, everything, is about 600 exajoules. That's 6 followed by 19 zeros. It's a number so large that it's almost incomprehensible. To accelerate a spacecraft of reasonable size to even 0.1% the speed of light, That's 1/10 of 1%. We'd need something like 10,000 to 100,000 exajoules. That's not something we'll do next year or next century or next millennium. That's a fundamentally different scale of energy production than anything human civilization has ever achieved or even seriously planned for. We're not talking about running out of technology or money or will. We're talking about the fact that the energy requirements are so enormous that they would require mobilizing the resources of the entire planet for centuries. And here's the really frustrating part. This isn't a technology problem that we can engineer our way out of using clever innovation. This isn't something that will be solved by the next breakthrough in battery technology or material science. This is a thermodynamic problem. This is physics. Newton's second law. F equals ma. Conservation of energy. These are the foundational laws of how reality works. They're not suggestions. They're not guidelines. They're hard limits. Some people get excited about antimatter propulsion. I understand the appeal. Antimatter is the stuff of science fiction. It sounds exotic and powerful and futuristic. When matter and antimatter collide, they annihilate each other and convert entirely into energy according to Einstein's equation E equals mc squared. This is theoretically the most efficient fuel possible. If you had a spacecraft powered by antimatter annihilation, you could theoretically achieve velocities that would make interstellar travel seem more feasible. But here's the problem. We can barely make any antimatter. The total amount of antimatter humanity has ever produced could be measured in nanograms. Billionths of a gram. The largest amount we've ever created in a single experiment is something like 10 billionths of a gram. And it's incredibly difficult to make and incredibly dangerous to store. A single gram of antimatter would cost about $100 million to create with our current technology. And to fuel an interstellar spacecraft, we'd need kilograms. Thousands of kilograms. That would cost hundreds of trillions of dollars. Far more than the entire economic output of human civilization. And that's assuming we could even contain and store antimatter safely, which we can't. Not yet. Not reliably. Not in the quantities we'd need. Antimatter and matter annihilate each other on contact. So you'd need to keep the antimatter completely isolated, suspended in a magnetic field, floating in a vacuum. Any power loss, any equipment failure, and the whole thing goes up in an explosion that would make a nuclear weapon look like a firecracker. What about nuclear fusion? Fusion is the process that powers the sun. It's the most powerful energy source we know of besides antimatter annihilation. We've known how to do it since 1942. We can build hydrogen bombs with fusion. They're some of the most powerful weapons ever created. But controlling fusion for peaceful purposes, creating a sustained fusion reaction that produces more energy than it consumes, that's been 30 years away since 1950. We're still working on it. The International Thermonuclear Experimental Reactor in France is trying to achieve net positive fusion power. And it's just a really hard problem. Fusion requires heating plasma to hundreds of millions of degrees and containing it in a magnetic field. The engineering challenges are enormous. We're still not there. We probably won't achieve sustained net positive fusion for another 20, 30, maybe 50 years. And that's optimistic. And even if we do, we'd need to scale it up to power an interstellar spacecraft, which would be an even more difficult engineering challenge. So antimatter is too expensive and we don't know how to make it in quantity. Fusion is too difficult and we haven't solved it even for stationary reactors on Earth. What about chemical rockets? They're powerful in short bursts, but they'd run out of fuel long before reaching interstellar speeds. A chemical rocket can accelerate a spacecraft for maybe 20 minutes before it burns all its fuel. You can't sustain acceleration for years on chemical rockets. Solar sails might work for very light probes, using light from the sun to push a thin mirror, but they wouldn't carry people. They'd be incredibly slow and would take centuries to reach any useful velocity. Ion drives are theoretically efficient but produce tiny amounts of thrust. You're looking at acceleration measured in millimeters per second squared. That's 1,000th of the gravitational acceleration you experience standing on Earth. There's no silver bullet. There's no propulsion technology on the horizon that changes these fundamental constraints. We've looked at all the major possibilities: chemical, nuclear, fusion, antimatter, solar sails, ion drives, and various exotic possibilities. and none of them can get us to the speeds we need in any reasonable time frame. Let's say we solve the energy problem somehow. Let's say some future breakthrough in physics gives us access to a new source of power. Let's say we invent a propulsion system that can accelerate a spacecraft to 10% the speed of light. That's incredibly fast, over 30,000 kilometers per second. That's 500 times faster than our fastest current spacecraft. At that speed, reaching Alpha Centauri would take 43 years. That's a lifetime. It's a full human lifetime of travel. You'd spend nearly half a century in a spacecraft, and the astronauts would arrive only to find that they couldn't stop. They'd have to keep going because slowing down would require energy, and they've used all their energy getting there. You'd reach your destination and then just keep flying past it. But okay, let's assume we solve that too. Let's assume we have a spacecraft that can somehow accelerate to 10% the speed of light and then decelerate on the other end. That means you need to carry twice as much fuel, half to speed up, half to slow down. You'd leave Earth when you were 20 years old. You'd arrive at Alpha Centauri when you're 63 years old. That's the best case scenario. And when you arrive, everyone you ever knew on Earth? Dead. Your family? Gone. Your great-great-grandchildren might still be alive, but they would have no memory of you or knowledge of your life. The whole of human civilization would have moved forward by 43 years. Technology would be unimaginably advanced. The world would be different. Languages might have changed. Governments might have fallen and risen. Cultures would have evolved in ways you couldn't predict. And now multiply that across generations. If you wanted to establish a self-sufficient colony at another star system, you'd need to send multiple waves of colonists. Ships would need to leave Earth every few years for decades or centuries to build up enough population at the destination. And here's where it gets really weird. People on both sides of the journey would be effectively time-traveling relative to each other. The people on Earth would age differently from the people in the ships. Think about this scenario. You send the first wave of colonists to Alpha Centauri. They leave in the year 2100. They arrive in 2143. That's 43 years for them. Now you send the second wave in 2110. From Earth's perspective, it's only 10 years later. But from the perspective of the first wave, only 7 years have passed. The first wave colonists would receive a message from Earth saying that the second wave is being sent, but that message would take 4.37 years to get there. And then their response would take another 4.37 years to get back. You're looking at communication delays measured in decades. Relationships would be impossible. Family connections would be severed by the sheer physics of space and time. This raises a profound philosophical question. Why would any individual human being agree to spend most of their adult life in a spacecraft to reach a destination they would never truly understand? You'd never get to know the star system. You'd spend your whole life in a metal can. The view out the window would be mostly black. You'd be born, grow up, age, and die, all in the same enclosed environment. Your entire existence would be transit. Your entire life would be defined by the journey, not by the destination. That's not an adventure. That's not exploration. That's confinement with a purpose that you might not even live to see fulfilled. And this assumes that we've solved all the biological problems of long-duration spaceflight, which we absolutely have not. Astronauts who spend months in space experience bone loss, muscle atrophy, vision problems, and immune system degradation. It's brutal. The human body evolved over millions of years in a specific environment, Earth. We need 1 g of gravity, the gravitational acceleration you experience on the surface of the planet. We need an atmosphere of the right composition. We need a day-night cycle. We need a planet's magnetic field protecting us from radiation. None of those things exist in interstellar space. The radiation alone is a serious problem. Cosmic rays from beyond our solar system are constantly bombarding everything in space. They're high-energy particles that can damage DNA and increase cancer risk dramatically. On a journey of decades or centuries, the accumulated radiation exposure would probably give any crew serious health problems. We have no proven way to shield against this radiation without carrying so much shielding material that the spacecraft becomes too heavy to accelerate to any reasonable speed. You're stuck in another catch-22. Here's something most people don't think about when they imagine interstellar travel. The faster you go, the weirder reality gets. This isn't philosophy. This isn't my opinion. This is Einstein's special relativity, and it's as fundamental to the universe as gravity. It's been tested, verified, and confirmed countless times. As you accelerate closer to the speed of light, time itself slows down relative to stationary observers. This is called time dilation, and it's not a thought experiment. It's been measured and verified. We've put atomic clocks on airplanes and measured the difference. Astronauts in orbit age slightly slower than people on Earth. Not by much, but measurably. Now imagine accelerating to half the speed of light. At that speed, time would slow down to 86% of the normal rate for someone on the spacecraft. A year for you would be 1.16 years for everyone on Earth. You'd arrive at your destination having aged slower than the people back home. That's manageable, okay. But here's where it gets really weird. As you approach the speed of light, time dilation becomes increasingly extreme. At 99% the speed of light, time slows down to 7% of the normal rate. A full year for you would be 14 years on Earth. At 99.9% the speed of light, time slows to 2.2% of normal. A single year for you would be 45 years on Earth. You're barely aging while decades pass back home. This creates a genuinely bizarre situation. Let's say you want to travel to a star that's 100 light years away. You accelerate to 99.9% the speed of light. From your perspective, time dilation means you'd arrive in just 7.1 years. You'd age 7.1 years. You'd leave Earth at age 20, and you'd arrive at a distant star at age 27. You'd barely feel like you'd aged at all. But here's the catch. Everyone on Earth would have aged about 100 years. You'd arrive to find that everyone you ever knew, everyone you ever loved, everyone you ever will ever know, would be dead for generations. Your family would be long extinct. Your country might not even exist anymore. Human civilization as you knew it would be gone. You'd be traveling backward through time in a very real sense. You'd arrive in a world that's 100 years in the future relative to you. You'd be a time traveler. Now, relativity also tells us something else. The faster you're moving, the more massive you become. This is called relativistic mass. It's a weird property of the universe, but it's real and it's been verified. As you approach the speed of light, your apparent mass increases. At 99% the speed of light, your mass increases by a factor of about 7. So if you weigh 70 kilograms at rest, at 99% the speed of light, you'd have the inertia of a 490 kilogram object. This means it would be even harder to accelerate further. It would require exponentially more energy to push you any faster. And there's a hard limit to all of this. The speed of light is not just the fastest speed you can travel. It's a cosmic speed limit. Nothing with mass can reach the speed of light. You can get arbitrarily close to it, 99.9%, 99.99%, 99.9999%, but you can never actually reach it. The energy required to accelerate just 1 more micrometer per second approaches infinity. This isn't a limitation of our technology. This isn't something we'll overcome with better engineers or more funding. This is a limitation of the universe itself. It's built into the fabric of reality. So let's talk about what a realistic interstellar spacecraft would actually need to accomplish its mission. First, we'd need a spacecraft that's completely self-sufficient for decades or centuries. It would need to generate its own oxygen from water or atmosphere. It would need to produce its own food. Imagine being on a spacecraft where you're growing food in hydroponic gardens, recycling your own water, scrubbing carbon dioxide from the air. You're completely dependent on these systems for survival. If they fail, you die. It would need to treat waste, both human waste and the byproducts of all the systems running on the spacecraft. It would need to handle repairs when things break, and things will break. We know this from long-duration spaceflight on the International Space Station. Things are always breaking. Pump fails. A sensor goes haywire. Equipment degrades. You need spare parts, redundant systems, and people who know how to fix things. And you can't send a repair crew up from Earth. You can't call for technical support. You're on your own. We've never built a closed-loop life support system that works reliably for more than a few years. The ISS constantly receives resupply missions from Earth. Supplies come up regularly. Fresh food, water, spare parts, new equipment. If the ISS's life support system fails, they can usually fix it or they can survive until a resupply mission arrives. But if we sent a spacecraft to another star system, we wouldn't have that option. We'd be entirely alone. Any system failure could be catastrophic. And the longer you're in space, the more likely it is that something will fail. Second, we'd need a propulsion system that can operate reliably for decades or longer. Not in short bursts like a rocket. Continuously, providing steady acceleration. We don't have any propulsion system that does this. We have ion drives that can operate for years. They're actually quite reliable, but they produce tiny amounts of thrust. You'd accelerate so slowly that it would take decades to reach meaningful velocities. Chemical rockets burn their fuel in minutes. That's not going to work. Nuclear reactors are heavy and require shielding and maintenance. A fusion engine would be theoretically perfect, but we can't even make fusion work on Earth yet. Third, we'd need some way to protect the crew from radiation. This is a genuinely hard problem. In low Earth orbit, we have the Van Allen radiation belts to contend with, but the Earth's magnetic field provides significant protection. Beyond the Earth, cosmic radiation becomes a serious threat. We're talking about high-energy particles from outer space, cosmic rays, that can damage DNA and increase cancer risk dramatically. They can cause cataracts, immune system problems, and central nervous system damage. Shielding against this requires thick walls of material, lead, water, polyethylene. But every kilogram of material we add to the spacecraft makes it harder to accelerate. You're stuck in a catch-22. Make the spacecraft heavier to protect the crew, and you need more energy to accelerate. Use less shielding to reduce weight, and the crew gets exposed to more radiation. There's no good solution. Fourth, we'd need some way to brake when we arrive at the destination. This is often overlooked. It's easy to talk about accelerating to 10% the speed of light, but how do you slow down? You can't just flip a switch. You can't deploy a parachute in the vacuum of space. You need to expel mass or use some propulsion system to decelerate. This means you need to carry enough fuel or reaction mass to decelerate at the end of the journey. For a really fast journey, this doubles or triples your fuel requirements. You need fuel to speed up and you need fuel to slow down. You're carrying an enormous amount of mass just to decelerate. Fifth, we'd need to handle navigation and course correction. Interstellar space is not empty. There are dust clouds, asteroids, and other hazards scattered throughout. Traveling at 10% the speed of light, 30,000 kilometers per second, even a grain of sand would hit with tremendous force. It would be like a bullet traveling at cosmic speeds. We'd need some kind of shield or detection system to avoid collisions. We'd also need to navigate, which means we'd need accurate star charts and some way to orient ourselves in space and correct our course if we start drifting. Sixth, and this is crucial, we'd need some way to handle the psychological and social challenges of long-duration spaceflight. Studies from the ISS and from submarines show that humans can develop serious mental health problems during isolation in confined spaces. Depression, anxiety, interpersonal conflicts. Over decades or centuries, these challenges would be multiplied enormously. You'd need training programs, psychological support, entertainment, culture, religion, meaning. You'd need to maintain social bonds across multiple generations born in space who have never seen Earth. They've never felt rain. They've never seen the sky at sunset. They've never stood on soil or felt wind or experienced the smell of rain. This is not a trivial engineering problem. This is a fundamental human problem. You're asking people to live their entire lives in a confined space with the same people, doing the same activities, looking at the same walls. How do you maintain mental health? How do you prevent social breakdown? How do you keep people motivated to maintain critical systems when the payoff is something they might never see? Now, despite all these obstacles, scientists haven't given up. They're still proposing ways that humanity might one day reach another star. Some of these ideas are clever. Some of them are desperate. Let's talk about them because they show just how creative and just how desperate we have to be when we think about this problem. There's an idea called the interstellar ramjet. This was proposed by physicist Robert Bussard in 1960. The idea is elegant. You accelerate to high speed, and then you use an electromagnetic field to scoop up the thin hydrogen that exists between stars and use it as fuel for a fusion engine. This would theoretically let you travel at relativistic speeds for indefinite distances without carrying massive amounts of fuel. You'd be using the fuel of the universe itself. The problem? We don't have the technology to do any of this. We can't make a fusion engine. We can't create an electromagnetic field powerful enough to scoop up hydrogen from interstellar space and compress it into a reactor. And the Bussard ramjet might not even work. There are serious theoretical problems with how it would actually function. As you get faster and faster, the drag from scooping up hydrogen becomes greater. At some point, the drag exceeds the thrust from the fusion reactor. You can't go any faster. You reach a terminal velocity and you're stuck there. There's the idea of the solar sail. A spacecraft covered with ultra-thin mirrors could be pushed by light from a powerful laser back on Earth. This has actually been demonstrated at small scales. In 2019, a solar sail called Light Sail was deployed and successfully demonstrated that light can provide thrust. It's one of the few propulsion concepts that doesn't require any fuel to be carried on the spacecraft. The energy comes from Earth. The problem is that it's slow. A solar sail could theoretically reach high speeds eventually, but it would take years or decades of acceleration. And you'd need lasers more powerful than anything we've ever built. We're talking about a 100 gigawatt laser array. For perspective, the entire electrical power generation capacity of the United States is roughly 1,200 gigawatts spread across the entire country. A 100 gigawatt laser would be massive. The energy requirements are astronomical. There's the concept of suspended animation or cryogenic sleep. If astronauts could be frozen for the duration of a long journey, they wouldn't age, they wouldn't experience psychological strain, and they wouldn't need to eat or consume resources. The appeal is obvious. You put people in hibernation, and they sleep their way across the stars. The problem is that we have absolutely no idea how to do this safely. Freezing humans causes ice crystal formation that destroys cells. We've never successfully thawed a human being from full cryogenic suspension. We've frozen some mammals and revived them, but only after relatively short periods. Some bears and ground squirrels can enter a form of hibernation naturally, but humans don't have that ability. Freezing a human for decades or centuries is pure science fiction at this point. We don't have the technology. We don't know if it's even possible. There's the concept of generating gravity on a spacecraft through rotation. A rotating spacecraft would create artificial gravity through centrifugal force, which would help preserve astronaut health during a long journey. This is theoretically possible and has been understood since the early days of spaceflight. You spin the spacecraft, and the centrifugal effect creates an outward force that feels like gravity. The problem is that building a large rotating spacecraft is incredibly expensive and complex. You'd need a spacecraft that's hundreds of meters in diameter to produce meaningful gravity without making people dizzy. People have a threshold of sensitivity to rotational effects. If the rotation is too fast, people get disoriented and nauseous. To produce 1 g of gravity, you need a radius of about 224 meters and a rotation rate of about 1.3 revolutions per minute. That's a huge structure. We haven't built anything like this yet. There's the concept of the generation ship, where multiple generations would be born and die on the spacecraft before reaching the destination. This is maybe the most realistic concept, in that it doesn't require any technology we don't already have. You just need a habitable module that's large enough to house thousands of people, with food production systems, water recycling, and all the other necessities of life. But it requires something arguably more difficult. It requires a civilization willing to commit to a project that will take hundreds or thousands of years to complete. It requires societies to remain stable and focused on this mission across centuries. It requires people to accept being born in space and never seeing Earth. In the context of human history and human nature, this might actually be the hardest part. Throughout human history, our societies have been unstable. Empires rise and fall. Political systems change. Religions come and go. The idea that a single organization could maintain focus on a goal for 500 or 1,000 years seems almost impossible. There are fringe ideas too. Warp drives, wormholes, time travel. These are based on general relativity, which does permit these phenomena in principle. Einstein's equations do have solutions that describe warp drives and wormholes, so theoretically they're not impossible. But here's the problem. Building a warp drive would require more energy than exists in the observable universe. It would require negative mass, exotic matter that pushes rather than pulls. We've never observed negative mass. Probably doesn't exist. Wormholes would require threading a tunnel through spacetime itself, which sounds like something out of Star Trek. We have no idea how to do this or if it's even possible. These aren't just beyond our technology. They're beyond our understanding of how reality works. Here's what changed in the scientific community. For decades, scientists spoke about interstellar travel as something that was difficult but ultimately possible. Just a matter of more funding, more research, more innovation. In the 22nd century, we'll be crossing the stars, they'd say. Given enough time and resources, we'll figure it out. There was an assumption that any problem could be solved with technology. But something has shifted in the scientific community in the last 10 to 15 years. As physicists and engineers have done the mathematics more carefully, as they've thought through the engineering challenges in more detail, as they've consulted with each other and pooled their knowledge, a different picture has emerged. It's not that interstellar travel is hard. It's that the laws of physics might make it genuinely impossible. The constraints aren't engineering constraints. They're physics constraints. And physics is not negotiable. Consider the Fermi paradox. It's a famous question in the search for extraterrestrial life. It was formulated by physicist Enrico Fermi in 1950. The basic question is simple but profound. If the universe is so vast and so old, where is everybody? If intelligent life is common, we should have encountered evidence of it by now. Alien transmissions, alien probes, alien von Neumann machines that have spread across the galaxy. Something. And one possible answer, one that more and more scientists are considering seriously, is that space is simply too vast and too empty for interstellar travel to ever be practical. The distances are so great that traveling between stars is fundamentally, insurmountably difficult. If that's true for us, it's probably true for aliens too. Maybe that's why we don't see evidence of advanced aliens. They're all stuck on their home planets, just like we're stuck on ours, realizing that the universe is just too big to cross. They've gone through their own scientific revolutions. They've asked their own Fermi paradox questions, and they've reached the same conclusion we're reaching. Astrophysicists have started running detailed models to see what a realistic interstellar mission would look like. The results are sobering. Even with incredibly optimistic assumptions about future technology, assuming we solve fusion, assuming we get exponentially better at everything, assuming a future civilization has resources we can barely imagine, the energy requirements remain astronomical. The time requirements remain longer than human lifetimes. The engineering challenges remain profound. In 2018, a paper published in the Journal of the British Interplanetary Society modeled what an interstellar mission might actually look like with assumptions about future technology. The conclusion was stark. To send a crewed mission to Alpha Centauri in any reasonable time frame would require a spacecraft so large, so massive, so expensive, and requiring so much energy that it's effectively impossible for any civilization based on a single planet. You'd need to mobilize the resources of an entire planetary civilization for decades or centuries just to build the spacecraft. You'd need to redirect the entire output of human civilization to this single project. And then, after all that effort, after centuries of preparation and resource allocation, the astronauts would arrive at a destination that's almost certainly empty or devoid of anything useful. Alpha Centauri is a star system with potentially 3 planets. We don't know if any of them are habitable. We don't know if they have liquid water or breathable atmospheres. We don't know if they have resources worth the effort. You'd spend centuries of human civilization's energy to reach a star system that might be completely worthless. Another factor that scientists are beginning to acknowledge is the sheer waste of effort. If we launched a spacecraft to Alpha Centauri today, technology on Earth would advance so rapidly that by the time the spacecraft arrived 43 years later, a probe launched a century later using technology developed in the interim might get there first. Or even multiple probes. The technology gap would be so large that a smaller, newer probe could catch up and overtake a ship that left earlier. The spacecraft becomes obsolete before it even completes its mission. All that effort, all that time, all those resources, and the data you bring back would be superseded by something better. It's like building a massive library when the internet is being developed. It's inefficient, it's wasteful, and there's a philosophical question underlying all of this. Why would we even want to? Alpha Centauri is a star system with potentially 3 planets. We don't know if any of them are habitable. We don't know if settling there would be any better than staying on Earth. In fact, Earth is uniquely suited for human life. It's our home. We've evolved here over millions of years. Our biology is perfectly adapted to Earth's environment. Traveling to another star system and trying to establish a colony would be exponentially harder, exponentially more expensive, and exponentially more dangerous than maintaining our presence here on Earth. If interstellar travel is impossible, what's the realistic next step for human expansion? The answer might be humbler, but it's also more achievable. We need to settle near space first. We need to establish permanent settlements on the Moon and Mars. We need to build space stations in Earth orbit and in other locations around the solar system. We need to mine asteroids and establish resource centers. This is not as glamorous as star travel, but it's actually possible with technology we either have or are close to developing. The Moon is 384,000 kilometers away. That's about 9 days of travel in our current spacecraft. Realistic, achievable. We've been there before. Kennedy said we'd go to the Moon in the 60s, and we did. Now we should go back and stay. We should establish a permanent base. We're probably 5 to 10 years away from having technology that could support this. We need better rovers, better habitats, better life support systems. But nothing on the Moon requires us to violate physics or build technology that's fundamentally beyond our reach. Mars is 55 million kilometers away at closest approach. That's a 6 to 9 month journey with current technology. Difficult, but not impossible. SpaceX, NASA, and other space agencies are developing the technology to send humans to Mars. It's a massive engineering challenge, but it's achievable. We're probably 20 to 30 years away from the first crewed landing. And once humans are on Mars, once we've established a self-sufficient colony there, that opens up the possibility of settling elsewhere in the solar system. The asteroid belt contains millions of asteroids made of rock, metal, and ice. These are potential sources of water, metals, and other resources. A civilization that has settlements on the Moon and Mars could gradually expand to mine asteroids, establish orbital stations, and create a network of human settlements throughout the inner solar system. Over hundreds or thousands of years, this could develop into a true multiplanetary human civilization. Some scientists have speculated about megastructures like O'Neill cylinders, massive rotating habitats in space that could house millions of people. These are theoretically possible using materials we can get from asteroids. They're not easy to build, but they're not impossible. Over centuries, humanity could potentially establish billions of people living in artificial habitats throughout the solar system. That's not interstellar expansion, but it's still a profound expansion of human civilization. But these projects are still local in cosmic terms. The furthest we could realistically expand in the next 1,000 years is perhaps to Jupiter's moons or Saturn's moons. In the context of the galaxy, that's nothing. We'd still be confined to our tiny little solar system. We'd still be unable to reach the nearest star, which is 4 light-years away. But it's realistic, it's achievable, and it would represent an incredible expansion of human civilization. Okay, let's play a thought experiment. What would it actually take to make interstellar travel happen? What would have to change? What technologies would need to be invented? And what would it cost? Let's be realistic about it. First, we'd need a working fusion engine. Not just working in theory or in a lab. We'd need a functioning, reliable fusion reactor that could be installed on a spacecraft and operate continuously for years without failure. We're probably at least 20 to 30 years away from having a prototype that works. We're probably at least 50 to 100 years away from having something reliable enough to put on a spacecraft that we trust with human lives. And we'd need to produce these engines in quantity. Not just one, dozens, maybe hundreds. Second, we'd need some kind of radiation shielding that doesn't require carrying tons of material. Maybe using electromagnetic fields generated by the spacecraft to create a protective bubble. Or maybe developing materials we don't yet know about. Materials that are lighter and more effective than anything we currently have. This requires material science breakthroughs that we can't predict. We don't know what they are or when they'll happen. This is a real unknown. Third, we'd need closed-loop life support systems that can operate reliably for decades or longer. We'd need to grow food on the spacecraft. We'd need to recycle water and air and waste. We'd need to maintain these systems with minimal external input. We're getting better at this through projects like the ISS, but we're still not there yet. We're still learning. Fourth, we'd need affordable mass production of spacecraft. To send multiple generation ships to different star systems, you'd need to be able to build them in quantity. This would require manufacturing capabilities we don't currently have. You'd need the ability to build massive spacecraft, kilometer-scale structures, in a cost-effective manner. Fifth, we'd need breakthroughs in material science, computing, robotics, and medicine. We'd need artificial intelligence sophisticated enough to maintain a spacecraft and help manage the social problems that arise during a multi-generational journey. We'd need medical technology advanced enough to handle health crises in isolation. We'd need robotic systems that can perform repairs and maintain the spacecraft with minimal human intervention. And here's the thing that's crucial. None of these are just engineering problems. They're not just we need to spend more money and we'll figure it out. Some of these are fundamental scientific problems. We don't fully understand how to achieve stable fusion. We don't know how to create effective radiation shielding for long-duration space missions. We don't know if suspended animation is possible. These aren't engineering problems. These are science problems. And science takes time. You can't force scientific breakthroughs with money or willpower. The cost would be astronomical. And I don't mean that metaphorically. The cost of building, launching, and operating an interstellar mission would probably be hundreds of billions or trillions of dollars. For perspective, the total military spending of the United States in 2024 was about $800 billion. An interstellar mission would cost more than that, probably multiple times more. For a developed nation, that's essentially impossible. It would require a level of commitment and resource allocation that's simply not realistic in our current political and economic system. Let me be very clear about something. Some of the constraints we've been discussing can't be overcome with better technology. They're not engineering problems. They're physics problems. And physics, unlike engineering, is not negotiable. You can't innovate your way around Newton's laws or Einstein's relativity. You can only work within them. That's the fundamental difference. The speed of light is a universal speed limit. Nothing goes faster. Not with any conceivable technology. Not now. Not ever. This is not a limitation of our current understanding. It's fundamental to how the universe works. The structure of space-time itself forbids faster-than-light travel. Relativity tells us that moving faster requires exponentially more energy. And at the speeds necessary for interstellar travel, the energy requirements become absurd. Conservation of energy tells us that you can't create something from nothing. If you want to accelerate a spacecraft to 10% the speed of light, you have to use energy. Real physical energy. That energy has to come from somewhere. It has to be generated, stored, and released. The math on this is inescapable. The numbers don't work. Thermodynamics tells us that entropy always increases. This means that any closed system will gradually decay. A spacecraft is a closed system. Over decades or centuries, things will break down. Entropy will increase. You can delay this process with maintenance and repair, but you can't stop it. Sooner or later, systems will fail. The entropy law is inexorable. And then there's the biological constraint. Humans are adapted for Earth. We need 1 g of gravity, an atmosphere of oxygen and nitrogen, a day-night cycle, and protection from radiation. None of those things exist in a spacecraft or in interstellar space. You can create artificial versions of some of these, but not all. And maintaining them requires energy and resources. It's hard. It's really hard. Some scientists have speculated that the solution might be to modify humans genetically or cybernetically to adapt them for space. Maybe we could create humans who don't need as much gravity, who can survive radiation exposure, who can live in low-pressure environments. Maybe we could replace biological systems with mechanical ones, create cyborgs optimized for space travel. This opens up all kinds of philosophical questions. Is a being that's been modified that extensively still human? At what point does post-human modification become something else entirely? Are we still talking about humanity, or are we talking about creating a new species? These are profound questions, and they're not just philosophical. They're ethical and they're practical. If we modify humans that extensively, are we still preserving human values? Or are we creating something new, something we might not understand, something that might not share our goals or our values? Here's something profound that most people don't think about. We're surrounded by hundreds of billions of stars in our galaxy alone, and the universe contains hundreds of billions of galaxies. It's vastly probable that intelligent life has emerged elsewhere in the universe. It's overwhelmingly probable. The statistics demand it. And yet, we don't see them. We don't hear them. There are no alien transmissions. There are no alien visits. There's no evidence of alien civilizations anywhere in the observable universe. This is called the Fermi paradox, and it's one of the most important questions in science. The Fermi paradox essentially asks, where is everybody? If intelligent life is common, we should have encountered it by now. But we haven't. We've searched the skies with our telescopes and our radio receivers. We've sent out our own signals, and we've heard nothing but silence. The universe appears to be empty. There are many proposed explanations. Maybe intelligent life is very rare. Maybe the emergence of intelligent, technological civilization is so unlikely that we're the only ones in the observable universe. Maybe intelligence always leads to self-destruction. Maybe there's a great filter, some stage in the development of life or civilization that most species don't pass. Maybe intelligent life is common, but it's all too far away for us to detect. Maybe they're deliberately hiding from us. Or maybe, and this is the explanation that's becoming more prominent in the scientific community, maybe interstellar travel is simply impossible, so every civilization that arises stays on its home planet. They're all out there, civilization after civilization, thinking about the stars, developing their own technology, conducting their own searches, but unable to cross the vast gulfs between them. Each civilization is trapped on its home planet by the same laws of physics that trap us. If that's true, then the universe is populated with civilizations that are utterly isolated from each other. Each one thinks it's alone. Each one wonders if intelligent life exists elsewhere. Each one sends out radio signals into the void, hoping for a response that will never come. It's a universe full of lonely voices calling out across the dark. This is a genuinely strange and sobering thought. The universe could be full of intelligent life, and yet every civilization would be effectively alone. Not because life is rare, not because intelligence is rare, but because space is too vast for anyone to cross. The universe could be teeming with consciousness and wonder, and yet each mind would be imprisoned on its home world, separated from every other mind by distances that are simply too great to traverse. Some scientists find this deeply depressing, a universe full of life but empty of connection. Others find it oddly liberating. If we're not going to meet aliens, if interstellar travel is not in humanity's future, then our focus should be on what we can actually do. Building a sustainable civilization on Earth, establishing settlements in near space, creating art and culture and meaning in the places we can actually reach. For centuries, humanity has looked at the stars with wonder and with the assumption that we would one day travel among them. It's been part of the human dream. It's in our stories, our myths, our science fiction. We've imagined great space empires and galactic federations. We've read about humans spreading across the stars like seeds on the wind. We've always assumed that the stars were calling to us. We've always believed that somewhere, eventually, we would answer that call. But what if that dream is fundamentally impossible? What if the universe is structured in such a way that intelligent life is forever confined to the planets that birthed it? How does that change human psychology? How does that change human culture? What does it mean for the human spirit? On one level, it's humbling. It teaches us that we're not as special as we might have thought. We can't just go wherever we want in the universe. We're constrained by physics. We're constrained by chemistry. We're constrained by biology. We're tiny, temporary creatures on a tiny planet in an incomprehensibly vast universe. And the universe doesn't care about our ambitions. It doesn't care what we want. It doesn't care about our dreams. But on another level, it can be profoundly meaningful. If Earth is our home, if we're not going anywhere, then we have a powerful incentive to preserve it and protect it. We have an incentive to build a sustainable civilization that doesn't destroy the planet. We have an incentive to create beauty and meaning in the place we can actually live. We have an incentive to take care of each other because this is all we have. It's also possible that the realization that we're isolated on Earth could unite humanity in a way that nothing else has. If we're all in this together, if we're all confined to the same planet, if we all share the same home, then the differences between us become smaller. National borders, cultural divides, political differences. These all matter less when you realize that you're part of a single species on a single world in an incomprehensibly vast universe. We're all passengers on the same ship, and that ship is Earth. The astronauts who have traveled to space and looked back at Earth have reported a transformative experience. They call it the overview effect. Seeing Earth from above, seeing it as a small, fragile, beautiful sphere of life floating in an infinite void, changes your perspective. It makes you realize how precious the planet is. It makes you realize how interconnected all life is on Earth. It makes you see humanity as a single species instead of separate nations and tribes. If humanity had a collective overview effect, if everyone could experience what astronauts experience when they see Earth from space, it might fundamentally change our civilization. Okay, so crewed interstellar missions are probably impossible. But what about sending robotic probes? What about sending small, unmanned spacecraft to explore other star systems? Surely that's more feasible, right? Surely we could at least do that? Well, yes, it is more feasible. In fact, there are a few serious proposals to do this. Project Breakthrough Starshot is one of the most credible. The idea is to create a very lightweight probe, just a few grams in mass, and accelerate it using a powerful laser on Earth. The probe would have no onboard propulsion. It would be pushed by light from a massive laser array. If successful, probes could reach nearby star systems in decades rather than millennia. The Breakthrough Starshot project is actually quite clever. The probe would be extremely light, essentially a chip with a tiny camera, a light sail, and some basic electronics. It would be pushed by a 100-gigawatt laser array on Earth. If the technology works, a probe could be accelerated to 20% the speed of light and reach Alpha Centauri in 20 years. That's incredible. That would represent a major achievement for human technology. A probe could reach another star system in human timescales. But there are significant challenges even with this approach. First, you need a 100-gigawatt laser. That's an enormous amount of power. For comparison, all the power generated by human civilization is about 20 terawatts. That's 20 million gigawatts. A 100-gigawatt laser would be tiny compared to human civilization's total output. But concentrating that power into a single laser array is a staggering engineering challenge. You'd need a laser array with an aperture of dozens of kilometers. You'd need to maintain that laser in space or on a mountaintop where the atmosphere is thin. It's not impossible, but it's incredibly difficult. Second, the probe would be so small and traveling so fast that it would be incredibly difficult to gather data from it. You'd have maybe a few seconds of interaction with the star system before the probe hurdles past it at 20% the speed of light. Taking pictures would be challenging. Getting meaningful scientific data would be even more challenging. What are you going to learn in a few seconds of interaction? Third, sending signals back from the probe to Earth across light years would be difficult. The probe would need to transmit a signal back to Earth using its tiny onboard antenna. That signal would be incredibly weak by the time it reaches Earth. You'd need a massive receiving antenna to detect it, and there would be a 20-year delay in communication each way, 40 years round trip. You send a command, and 20 years later the probe receives it. You wait for a response and another 20 years pass. But despite these challenges, Breakthrough Starshot is probably the closest we have to a realistic plan for interstellar exploration. It doesn't violate any laws of physics. The technology is difficult but achievable. If the project succeeds, we could launch